All right, now we're ready to talk about our examples. I just want to go through and do each of these example problems that I've laid out. So for number one, we want to do a pooled t-test. So remember that means that we're assuming that the population standard deviations are equal. And we're not even given the data, we're given all the important statistics for each of the data. So the sample mean, sample standard deviation, sample size. And so what we have to do is we have to go through and we have to use our formula. T is going to be x1 bar minus x2 bar, so that's 10 minus 12, over our pooled standard deviation, which we'll have to figure out in a second. Okay, so that'll go here, and then times the square root of 1 over 15 plus 1 over 15, 1 over n1 plus 1 over n2. So we just have to figure out our pooled standard deviation, and just following a formula, that's going to be n1 minus 1, so it's 14, times our s1 squared, so that's times 2.1 squared, plus n2 minus 1, so that's again 15 minus 1 or 14, times 2.3 squared, all over 15, so n1 plus n2 minus 2, so 15 plus 15 minus 4. It's really the sum of those two values that we get, so that's 28. Okay, so in the denominator. And it turns out when we plug all this in, our pooled standard deviation is going to be 2.2023, at least to 4 decimal places, so that goes here, 2.2, so 2.2023 times square root of what turns out to be 2 over 15. And it turns out that that's going to give us, so our test statistic is going to be negative 2.4870. Okay, so that's what we get. Remember that this is a two-tailed test, so that means, of course, our null hypothesis is always that the two population means are equal. Our alternative hypothesis, if it's two-tailed, means that they're not equal. And what remains now is to figure out our critical values. And our critical values are going to be the cutoffs, where we're going to have plus or minus t sub 0.025. We have 28 degrees of freedom, so that's going to work out to plus or minus 2.0484. Okay, and so what we're going to have, if we draw just a little picture here, we have our cutoffs, negative 2.4, 2.04, negative 2.04. We have negative 2.487. So our test statistic is somewhere over here. That's clearly in the rejection region, so we are going to reject the null hypothesis. Okay, and that's how that works. It's that simple. Next up, let's find a 95% confidence interval. So our confidence interval is going to be 10 minus 12 plus or minus, so x1 bar minus x2 bar, plus or minus our critical value, which is 2.0484, times the pooled standard deviation, 2.2023, times the square root of 1 over n1 plus 1 over n2. Okay, and so this turns out to be negative 2 plus or minus 1.6473. Or you can write it as an interval if you like. You can write it as the interval from negative 3.6473 all the way to 0.3527. Okay, assuming that I just did the subtraction correctly there. Okay, and that's all we have to do for the confidence interval for everything else. Okay, so there's our confidence interval, and we're done. So that's number one. Number two is going to be completely similar. It's just that we're going to have a left-tailed test or a two-tailed test. if we have a left-tailed test, remember what that means is that our alternative hypothesis is going to end up being that mu1 is less than mu2. And if we just go through everything, it's basically going to be the same thing here. We're going to end up with the test statistics. So that's going to be 7 minus 6.4 divided by the pooled standard deviation. The pooled standard deviation is going to be, I think it's just instructive to walk through it. It's going to be, let's see, we're going to have n1 minus 1, so it's 27, times s1 squared, that's 1.7 squared, plus n2 minus 1, so that's 36, times s2 squared, so it's 2.3 squared, all over, you can do 27 plus 36, or 28 plus 37 minus 2, however you want to think about it is fine. Okay, and so that's going to be our degrees of freedom for our denominator. Plug that in to your favorite calculating device, and you get 2.0643. So that's the pooled standard deviation. It turns out that your test statistic is going to end up being, so again, remember that the formula is that this is x1 bar minus x2 bar over the pooled standard deviation times 1 over n1 plus 1 over n2. So in our case, we get 7 minus 6.4 divided by 2.0643, okay, which was our pooled standard deviation, times the square root of 1 over 28 plus 1 over 37. Pop everything in. It turns out what you're going to get for your test statistic t is going to be 1.1604. Your critical value, if you think about the left-tailed test, your critical value is going to be the value where to the left you want an area of alpha, and so this is going to have a negative value. So this already tells you that we are not going to reject the null hypothesis. But our critical value, it turns out when you actually plug it in and calculate what you should get for your critical value, you get negative 2.38. Okay. And I don't know why I only have 2 decimal places there, but that's what I've written down. So negative 2.38. Okay. Our test statistic, again, this 1.1604 is somewhere over here. It's clearly in the do not reject region, so we do not reject. Okay, that's how that works. For part B, it's actually the same test statistic, same pooled standard deviation, and therefore same test statistic. All that changes is the critical value. And the critical value, if we have a two-tailed test, what we're going to do is we're going to look at plus or minus t sub 0, 0, 5, right? We take our alpha, we divide it in 2. We have 28 plus 37 minus 2 is, what is that, 63 degrees of freedom. And it turns out that if you look at the cutoff there, you're going to end up with 2.6561. Okay, and again, t is not outside the critical region there. It's between the two critical values, so we're going to have, again, 2.6561, negative 2.6561, and then our value is going to be somewhere in there. So we do not reject again. Okay, so do not reject. All right, third example, just moving right along here. For our third example, we're going to look at what we have as household vehicle miles traveled, which is something that the Department of Transportation compiles annually. And what we're going to do, there's a few different ways to do this test. I'm going to post a video showing you the magic that is the t.test function. I would strongly suggest that you learn how to use this and to use it well, because it is a huge time saver. Very, very helpful. And it's actually even helpful on some of the Chapter 9 problems that we were doing. But it's easier to explain now because it's really built for this 2 population mean test. So I would urge you to look up in R, just go to R, open it up, type in help parentheses t.test, and it'll bring up the documentation for this test. This test is awesome. It gives you basically everything that you need to know. if you don't know this test, what you can do is just use R as a calculator, so you do it the old way, and notice that we're just given two big sets of data. There's no reason to think that our populations have to have the same standard deviation. Maybe they do, maybe they don't, but we're not going to assume that they do. So we're not assuming that sigma 1 and sigma 2 are equal, so this is going to be a non-pooled t-test. Okay, so this will be non-pooled. So what that means is that our test statistic, t1, is going to be x1 bar minus x2 bar over the square root of s1 squared over n1 plus s2 squared over n2, and that's it. That's our test statistic. And it turns out that when you compute the means, the standard deviations, we know the sample sizes, what we're going to get for our t-value is going to end up being negative 0.924. Okay, so that's what we're going to get for our t-value. And then we need to compare that to our critical values. Remember that what we're looking at is we want to know, is there a difference between the Midwestern and the Southern households? Just is there a difference or not? So that means that this is a two-tailed test. Our null hypothesis is that the two means are equal, that mu1 is equal to mu2. Our alternative hypothesis is then that they're not equal. And we have a 5% significance level. So we're going to look at, so alpha is 0.05. So we're going to look at t sub 0.025. Those are our critical values. But we actually first need to compute the degrees of freedom. And the degrees of freedom, delta, is going to satisfy this crazy looking formula, remember. It's just kind of this ridiculous formula here. And so if you plug in our S1, S2, N1, N2 for our data set, it turns out what we're going to get for delta is this is going to be 26.344. So that means that our degrees of freedom will be 26, because you always round down, okay, to the next integer. And so if we have 26 degrees of freedom, then our cutoffs, t sub 0.025, are going to be plus or minus 2.05553, basically. So 2.0555. And our test statistic is in the do not reject region, so we do not reject. Okay, again, just to give you a little picture of that, we have 2.055. Here's my, as always, beautiful bell curve. So we have 2.0555, and likewise negative 2.0555. Okay, and we have our test statistic, negative 0.924, and that's in the right between the two critical values, so that means that we do not reject. Okay, that's our conclusion there. And chugging right along to number 4, it's going to be basically the same thing. Here we're going to be, here it's clear that we should use R. Okay, so there's really not too much more to say here, other than we should use R, and I'll show you a video on how to get this data in R very easily. But it turns out that if you look at the means, the standard deviations, the sample sizes, you end up with a test statistic that's negative 1.7207. Okay, you should do this on your own. You should just verify that this is all true, with 43 degrees of freedom. Okay, really our delta, was 43.8, and since we round down to the nearest integer, that becomes 43. Okay, our p-value, the t-dot test function, again, it's just magic. I love it. The t-dot test function, so this is help. Let me just write this a little bit more legibly. This is help t-dot test. Okay, and I don't know why my iPad is really into capitalizing. But there should be a lowercase help. Okay, and that's it. Okay, so go ahead and look up. The. I don't know where my colors went there, but go ahead and look up Oh, that's where they went. Look up that documentation. That'll be magic. Okay. That'll really tell us everything that we need. Okay, so help t.test gives us everything. Turns out our p-value is 0.094, 0.09236, 0.09236, so 0.0924. And we want to know what the 5% significance level, do we reject or not? Since our p-value is greater than alpha, in other words, since our alpha is less than or equal to p, that means that we do not reject. Okay, we do not reject the null hypothesis. Okay, and we're done with that. One more. This is a paired difference question. So this is a question from section 10.5. And the idea here is that, so Charles Darwin, the inventor is the wrong word, the discoverer of the theory of evolution, was studying cross-fertilization in the heights of plants and what effect that had on these particular plants called ZMAs plants. And what he did is he took 15 pairs of plants where one of the plants in the pair was cross-fertilized, the other was self-fertilized, and then he looked at their heights and he wrote down the differences of their heights. These differences are in eighths of an inch, okay? And that's the set of 15 differences that he has. So what he did is he wrote down these differences, and we want to know statistically, is there a difference between the cross-fertilized and the self-fertilized plants? Okay, so is there a statistical difference there? And we want to know at the 5% level, is there at the 5% significance level, is there a difference? What about at the 1% significance level? And it turns out that if we take this data, you can do all the usual things. If you were to take this data and you compute the t-value, the test statistic, you get d bar divided by the standard deviation of the differences over square root of n. And so when you plug everything in, it turns out that your means are going to be about 20.93333. Your standard deviation is 37.7, and n is 15, and you end up with 2.1480. Okay, I had R spit out that number exactly. R also tells us our p-value, and so our p-value is going to be, our p-value kind of ruins the story, actually, but our p-value is 0.0497. That means that to answer part A, at the 5% significance, we're going to reject the null hypothesis. There is enough evidence at the 5% significance level to reject the null hypothesis. At the 1% significance level, there's not enough evidence, so we do not reject the null hypothesis if we have a 1% significance level. Okay, and actually, when you type all this into R gives you a little bit more information than maybe you wanted, but it gives us also a confidence interval. In our confidence interval, it turns out, I didn't ask for this, but I could just add it in if I want a 95% confidence interval. Our confidence interval is going to turn out to be 0.0312 and 41.8355. So just finally, last thing in this video, the what the confidence interval tells you is there's a 95% chance that the difference, mu1 minus mu2, is in our confidence interval. Okay, so there's a 95% probability that mu1 minus mu2, the difference, is somewhere in that confidence interval. Okay? So that's the deal. That is all the magic of the t.test function. That's how everything works.